Hello everyone, this is Onindu Kumar Sharma. Today I will be presenting on Capsule Networks. This is a fascinating deep learning architecture that challenges the way machines traditionally process images and offers a new way to think about vision in AI. So let's dive a deep dive into a niche AI architecture. Convolutional neural network or CNN is the backbone of computer visions today. They are powerful, but they have a blind spot. They often lose spatial relationships between features. Take this example of a face. A CNN might label something like this as a face even if the eyes and mouth are jumbled, because it only detects the parts, not their arrangement. Capsule networks, introduced by Geoffrey Hinton in 2017, were designed specifically to address this weakness. Their key goal is to capture hierarchical part-whole relationships, allowing models to recognize not just features but how those features fit together. To place this in context, first in 1989, Leonard pioneered CNNs for handwritten digit recognition. Later in 2012, AlexNet revolutionized deep learning by massively improving image classification, fueling today's AI boom. Then in 2017, capsule networks were proposed as a way to fix these structural limitations of CNN. This shows how architectures evolve, from recognizing patterns to scaling up performance and finally to trying to understand the whole structure. The architecture of a capsule network starts with a convolutional layer, which extracts simple low-level features such as edges or curves. These outputs feed into the primary capsules, where neurons work together to produce vectors rather than scalars. The direction of a vector can encode pose like rotation or scale. From there, the information then passes to digit capsules, which represent the entire objects like a full digit or face. The critical mechanism is routing by agreement. If lower level capsules agree they are part of the same object, their signals are strengthened. If they don't agree, their influence is reduced. This allows CapsNets to build a richer understanding not just where parts are present, but how these parts are arranged. The core idea. To put it simply, a regular neuron gives a single number. On the other hand, a capsule gives a vector, which represents both whether something exists or how it exists. This pose, orientation or scales. This is like the difference between detecting that an eye is present versus knowing where that eye is facing. Routing ensures the correct part-whole relationships are reinforced, which makes the model far more robust to changes in future viewpoint. Capsule networks have shown promising results in experiments. On MNAST, they achieved an error rate of only 0.25%, which have outperformed traditional CNNs at that time. They also proved effective with fewer training samples, which is crucial when data is limited. A particularly strong result is that their ability to handle rotated digits. A CNN might mistake a rotated 6 for a 9, while a CapsNet correctly identifies it. These results show that capsule networks can capture structures in ways the CNNs cannot. Although capsule networks are still computationally heavy and are not widely used in practice, their influence is clear. They have inspired new research into models that go beyond raw detection and instead focus on understanding the whole relationships. Their potential impact is high in areas like medical imaging, where the arrangement of parts in a scan is critical, or autonomous driving, where recognizing objects in context is vital. The broader takeaway in this is the progress in AI doesn't only comes from making models bigger. Sometimes it comes from making them smarter, by designing them to reason about structure. To end with a simple phrase, perceptions is more than detection, and capsule networks are one step toward that future. Thank you all.